Hi, this short video is going to just recap a bit about distribution functions. It shouldn't take very long. Okay, so let's get starting. So first of all, what we need to think about is a thing called a random variable, and when we talk about these in general rather than specific values, we use large letters, uppercase letters. So let's call that capital Y. Random variable. Random variable is just a label, if you like, on an uncertain event. So if you're not sure there's an event and it could be in different states, you're not sure what state it's in, you can then label those states. So for example, maybe I will have a cup of coffee, or maybe I won't have a cup of coffee. I'm not sure yet. In the next hour, I'm going to label that state as no coffee would be y equals 0, and a coffee would be y equals 1. So it's just putting a number onto an event. So it's a labeling. And obviously in maths we like numbers and dealing with numbers rather than dealing with sort of words like have a cup of coffee and things. So random variable is just a label on an uncertain event. So here we are, and then the key concept to start with really is what's called the cumulative distribution function, and we can write that CDF. Yep. And what that is that we're going to write it capital F of little y, and that is just the probability that this random variable y, big one, is less than a specific value little y. So in statistical notation, the little Roman letters basically mean a specific value, an observed value. So if you're using data or got a specific value here, that's little y. When you see the large Y, that means a random variable called y. It's not specific. So this means probability a random variable called y is less than a specific value little y. And we're going to make that's a set of numbers from 0 to 1 basically as a function of y, and we're going to call that f of y. That's the cumulative distribution function. So that's the start. Oops. Now it's important to sort of distinguish then between what's called a discrete random variable or a continuous random variable. So if there's only a finite number of values or an infinite discrete values of the y's, integers say, we call that a discrete random variable. Alternatively, you could have a whole continuum of values, continuous, and they're called continuous random variable. Yep. So discrete one could be 0 and 1, binary, that's a classic one. It could be counts, it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, whatever. It could be cases of coronavirus, would be a discrete random variable. Continuous random variable, a good example would be something continuous like the height of a person, the temperature measured in Exeter, something that can take any value of the reals, and that's a continuous random variable. So can we then write this cumulative distribution function for these sort of things? So the discrete random variable, we can write f of y, we can write that as the sum, let's say x is less than or equal to y, f, little f of x. So basically all the values, the probability of getting y less than a particular value is just the sum of the probabilities of getting all the values x that are smaller than y. So f of y is the probability, let's write it this way, f of x is just the probability that the random variable y is equal to x, yeah? And this individual probability is called, this function little x is called the probability mass function. So we call that PMF. Yep. Right. So that's that one. continuous random variable, instead of having a sum, what we can do there for the continuous one, we don't have a sum, we replace that really with an integral up to little y, and then we have f of x dx. So here we had a sum over all the probabilities of the values smaller than little y. Here we do the integral. Yeah. You can't. It would be wrong to sort of say that little f of x here is the probability that y is equal to x, because if there's a continuum of values, so that's not true. If there's a continuum of values, there's an infinite number of little x values, so the probability for any particular one of them is pretty close to zero. It's slightly above zero, yeah. Infinitesimal, yeah. So it makes no sense to define it the same way here when it was discrete. So we can only define it more by the calculus. We say that instead it's the integral of little f gives you big F. So for instance, a particular temperature, 20 degrees in Exeter, the probability of that actually happening is almost zero. If you've got exactly 20.00000 degrees, the chance of ever that occurring would be close to zero. So you can't interpret it this way. What you can do is you can say f of x is df by dy, and that's from the fundamental theorem of calculus. So that's the way we define it for the continuous one. And this f of x here is called the probability density function, and that's called a PDF. So what we've seen here, we've had a cumulative distribution function. For discrete ones we have a probability mass function, and for continuous random variables we have a probability density function. So the cumulative distribution function is the sum, accumulated sum of the probability mass function. It's also the integral of the probability density function for continuous random variables. So that's pretty much it. I think I'll stop there. That hopefully makes that a bit clearer. Okay, thank you.